Hello everybody, this is the video clip for chapter 7 and this one is in section 7.3, which is one of the most important theorem in this course. Okay, this one is called a fundamental theorem of calculus. Okay, it is saying that if you have your function small f, okay, is integrable over the closed interval from a to b, and a capital F, it is also a function from a to b, from the closed interval ab to the real number r, satisfy the following conditions. Okay, the first one is that your f is continuous, okay, on the closed interval ab. The second one is your capital F is differentiable, okay, and your f prime, it is equals to the small f x for all x in the open interval ab. Then the integration from a to b of a function f, it is simply calculated by a capital F at b minus a capital F at a. Okay, so this one will help you in order to calculate the Riemann integration of a function small f. Okay, it is simply, instead of going through all the partitions and all that kind of thing, then we are just finding a capital F, okay, which is the derivative of this capital F equals to this small f. Then this integration can be evaluated by these two difference, okay, which is a difference of only a number. Okay, so let us prove this theorem. Okay, so we are going to use the again a Riemann criterion. Okay, that theorem 7.1.4. So we let your epsilon greater than 0. So by the theorem 7.1.4, we can have a partition, okay, let's say P, which is starting from x0 to xn, okay, of this closed interval AB, such that the upper sum of this partition over the function f, subtract the lower sum of the partition, the same thing, over the function f will be less than epsilon. Okay, so from the two condition here, which is number 1 and number 2, number 1 saying that your capital F is continuous, number 2 saying that your capital F prime equals to the F. Okay, so we use the mean value theorem, okay, for the capital F. All right, however, we use this one on each and every subinterval from xk minus 1 to xk. Okay, so it means that for each k, okay, in between 1 to n, we can have the point in between this interval, okay, open, such that your f at xk and f at xk minus 1, okay, the right end and the left end equals to f prime at the point in between, and then xk minus xk minus 1. Okay, however, from the condition number 2, this one, it is actually a small f at tk, xk minus xk minus 1. Are we all right? Okay, and because this t, it is within this interval, okay, so it means that in this interval, comparing this one, your f will be greater than or equals to the infimum, right? And also it will be less than or equals to the supremum. Okay, so your smaller m, it is the infimum of all the function value inside this interval, right? Xk minus 1 to xk, and then the capital M, it is simply this one, but instead of infimum we use the what? We use the supremum. Okay, so we know we know this kind of thing. So it means that your difference between these two function value will be less than or equals to a smaller mk, and then multiply by xk minus 1 and xk, and this one will be a capital MK and a difference of xk minus 1. This one, I'm sorry, the xk must be first, sorry, because it is greater. We just need to multiply by the length of each subinterval. Okay, so this one happen for each and every k from 1 to n. So what does this mean? It means that if we talking about a lower sum over this partition, which is a summation from k from 1 to m of a smaller mk, xk minus xk minus 1, okay, this one, from using this inequality, okay, it will be less than or equals to a summation from k to 1 to n, k from 1 to n of xk minus f at xk minus 1. Okay, and this one, from the next inequality, okay, it will be less than or equals to summation from 1 to n of capital MK xk minus xk minus 1, which will be of course this one, it is the upper sum of this partition, right? But can you remember this one? We did it several times, okay? Okay, if you looking at this one, we did it several times. As you expand it, it will give you f at x1, f at x0, and then f at x2, f at x1, and then f at x3, f at x2, right? And then etc. up to x at xn minus f at xn minus 1. Okay, so again, the first term previously will cancel the last term following. Okay, so this one, the first will cancel this one, and the first term here will cancel the last one on the next, and the first term somewhere here will cancel that last one there. So you end up with your f at the xn, which is a b, and f at an, which is the a. Okay, so right now, what is it that we have? Okay, we have that your LPF it is less than or equals to your FB minus FA, and then it is less than or equals to the upper sum of this partition over this function f as well. Okay, so we just keep this one in mind. Okay, keep this one in mind. Since f is integrable, so what does this mean? It means that the integration from a to b of this function, okay, is allowed to write, right? And this one, from the definition, okay, it is the infimum of all upper sum, so it will be less than or equals to, in particular, this upper sum, okay, for this partition. And again, by definition, it is a supremum of the lower sum. So in particular, if you compare with this lower sum for a particular p, partition p, then your integration of f, it is like in between these two values. Okay, so let us combine these two condition, I mean the relation together. We are going to have the integration from a to b of a function f, okay, minus your f B, this one, sorry, this one FB and FA, right? Your F at B, a capital F, and a capital F at A, okay? This one will be less than or equals to a U PF, right? Because this one, the inequality will reverse. So let me just do it this way. Okay, it will reverse, right, into a negative, okay, because you do a subtraction. So this one, it will be the L subtract the U, the U, the upper sum subtract the lower sum, okay, and this one will be the other way around, which is the lower sum subtract the upper sum, okay. However, from the beginning, we know that the upper sum minus the lower sum will always less than epsilon. So the other way around will be less than, will be greater than the negative epsilon. So it means that this absolute value, okay, among these difference, they are less than or equals to epsilon, no matter how small the epsilon is, okay, for any epsilon positive. Then what does this mean? It means that they cannot be something else, but they must be the same. So it means that this integration of your smaller f, it will be your capital F at B subtract your capital F at A, okay. So this is the first version of the fundamental theorem of calculus, okay. So it means that if you want to find this integrate, okay, the integration of x squared plus 1 from 0 to 1 of this function, okay, f, okay, then we let your capital F becomes x cubed over 3 plus x. Then we know that your f prime, it is like x squared plus 1, and your f is of course continuous, right, and it is already finding the derivative, right? So it means that by the theorem 7.3.1, which is the fundamental theorem of calculus, the first version, okay, we know that the integration of this function, okay, it is the same as capital F at 1 minus capital F at 0, and capital F at 1, it is simply 1/3, and 1 subtract 0 over 3 and 0, which is of course 0. So you got 4 over 3, okay, which will be comparatively simple rather than finding all the, you know, the partition. Even though you got the Riemann criterion, is still a little bit complicated. All right, so this is how we prove and use the fundamental theorem of calculus for the first version, okay. So next, let us talking about the fundamental theorem of calculus, but it is the second version, okay. For this one, okay, we saying that if your small f is an integrable function over the closed interval AB, however, this one, the capital F, it is defined to be the integration from a to x of this function ft dx, okay, dt, for all x in this closed interval from a to b. Then this capital F that defined this way is continuous, okay, this one. So this is the first assertion that your capital F defined using the integration like that, it is continuous on the closed interval from a to b. And the second assertion is that if your f, a small one, is also continuous at a particular point c inside this closed interval, your capital F is also differentiable at this point C, and a derivative of a capital F at this point C, it is equals to a small f, a function value of a small f at this point C as well. Okay. So for this one, then we are going to define this kind of function that construct it this way. Okay, if your small f from closed interval a b to real number r, okay, the so-called antiderivative of this small f on this closed interval a b is a function capital F, such that your f prime, okay, at each and every x equals to a smaller f of x, okay, for all x in this closed interval a b. If small f is integrable, then the function capital F, which is defined by this one, okay, the integration from a to x of function f, whenever your x is in this closed interval, this one is called the indefinite integral of a function small f in this closed interval a to b. Okay, so this one is just like to saying that the integration is somehow the operation that is an inverse of the derivative. Okay, this is somehow, roughly speaking, interpreted like that. Okay, so let us do some proof. Okay, so we let k be positive number, okay, be such that your f of x less than or equals to k. Why is that? We can start from this one. Don't forget that for this chapter, your f is always a bounded function. Okay, so by bounded function we can find this capital K that have this property, okay, for each and every x inside this domain closed interval from a to b. Okay, so the first assertion, we need to prove that your capital F is continuous at each and every point in this closed interval. So we let one point C in this closed interval, and we are going to claim that, okay, we claim that the limit as your x goes to C of this capital F equals to a capital F at the point C. Okay, this is the claim. So to prove that limit, we are going to let one epsilon positive, and then we are going to choose one delta, right, depending maybe on epsilon or something. Okay, and we let all the element x in this closed interval from a to b such that your x and c is not too far away. Okay, so it's the x minus c, that absolute value less than epsilon. Then we must calculate this one, okay, a difference between f of x and f of c, okay, which is simply the integration from a to x of ft dt minus the integration from a to c of ft dt. Okay, so this one we use the previous theorem on the previous video clip, okay, which is the theorem 7.2.4. okay, we can separate, right, the integration, okay, into two parts added together to get the larger interval. So this one, I mean, you just move it to the other way around to end up with your integration from x to c of the function ft dt. Okay, and then since your f always less than or equals the absolute value, okay, this one, your f always less than the absolute value f. Okay, so we use again the previous theorem from the previous video clip, which is the corollary 7.2.3. okay, to conclude that this one will be less than or equals to your f at t under the absolute value from x to c. Okay, and this one, it is actually by the bounded condition. Okay, this one will be less than or equals to the integration of x to c k dt, and this is simply a constant. So the integration of a constant will be simply equals to k, and then the absolute value of x minus c. Okay, actually, I mean, you can say c minus x, but this one, just to make it the same as what we have here, so I put the absolute value. And what is it that you need? You need to have this limit, right? So at the end, you need this one to be less than epsilon. So do you know how to choose the delta right now? Okay, so here is the connection between your delta and your epsilon, right? So you need to replace the absolute value of x minus c by delta, right? So your delta must be something that that involve the epsilon and the k, right? So this one we can use epsilon over k. Okay, so that this one less than epsilon over k, and then after you multiply by k here, you can cancel and let it, I mean, get it less than epsilon. So we have this claim. So it means that your capital F is actually continuous, okay, for each and every point on the closed interval from a to b. All right, so we must prove the second assertion. Okay, for the second assertion, we need to prove that your capital F prime at c, it is actually your small f at c. And this one, the derivative, okay, we are going to use this definition, okay, the limit as your h goes to 0 of f at c plus h minus f at c over h, okay, it must be equals to the small f at c. Okay, so this is our claim for the second assertion. All right, so we assume, okay, to prove the second assertion, you need to assume that your f is also continuous at one point c inside this closed interval. Okay, so this c and this c, they're the same, but maybe not the same as this one, okay, because the two assertion we already separate. Okay, all right. So for this one, let me just insert one more page. Okay, what is it that we know? We need to prove this limit, right? So we are going to, of course, given epsilon positive, okay, by the continuity, okay, by the continuity, we can find the eta, okay, instead of a delta, right? So we use another one, the eta epsilon, okay, such that if your x and c is not too far away, then your f of x and f of c, okay, also cannot too far away as well. It will be less than epsilon. Okay, so what is it that we have from here? Actually, we have x less than eta epsilon plus c, and also greater than negative eta epsilon plus c, right? And how about this one? this one we also have your f of x will be less than f of c plus epsilon, but it will be bigger than f of c minus epsilon. Okay, so this is what we have on each inequality that we interpret. Okay, now we are going to have the edge involved, and the edge must be something that pretty small, right? Because it will go close to 0. So your edge will not too far away from 0, right? So it will be less than this, I mean delta. But in this context, your delta, it is this epsilon, it is the eta epsilon, and it can never be 0 itself. Okay, so if this is your h, then your f is actually integrable on the smaller interval, right? Right now your f is integrable over the closed interval from a to b, but this one you can subdivide your a and b into smaller subinterval. For example, you can stop at c first, and then from a to also c plus h, okay, and then from c also to c plus h. Okay, so into several subintervals is still integrable on these subintervals. Okay, so let us calculate this one first. The numerator, f at c plus h, f at c, it is actually the integration from x to c plus h, right? I'm sorry, not from x, from a, right? Okay, of a small f minus from a to c of a small f. Okay, so again, using that theorem that you can separate the a and b, the closed interval a b, into several sub interval, right? So this one theorem 7.2.4. okay, we can conclude that this becomes a c to c plus h of ft dt. Okay, what happened to this one? What happened to this one? This one, your t, it is in between c plus h and c. Okay, so it look like this t coincide in this condition for x, right? So this t can be regarded as one of the x that has this condition. So immediately, if your t has that condition, the implication implies that your small f will be less than fc plus epsilon. So this one, it is less than your fc plus epsilon multiplied by h. What is it that you have here? What is it that you have here? So it means that your fc plus h, your fc over h minus your fc, you see, you divide by h first and then subtract by this one and take the absolute value will less than your epsilon, right? Which is this limit, is it? So it means that the limit as your h goes to 0 of this one exists, and it is equals to fc. But this limit, it is simply f prime at the point c. So you have f prime at the point c equals to a small f at evaluate at this point c as well. Okay, so we are done here. All right. So actually, please keep in mind that actually the real analysis, okay, is a pretty what do I say? A variety course. Okay, So you can have several approach, and you can also have several things to consider. For this one is only like maybe 25% or like 30% of all the real analysis that you actually can learn. Okay. However, we think that for you guys as an economist, okay, this one should be good enough for you to, you know, develop some kind of economic models and try to construct or inspire you something involve the economic terms, okay, using this kind of idea or using this kind of uh, analyze, okay, thinking. Okay, so we hope that you enjoy this course a lot, and we'll see you again when we have a chance. Bye bye.